Hello, again, my name is Gregory Plett, and I'm pleased to welcome you to this course on Introduction to Battery Management Systems. This course is the first in a specialization that investigates aspects of proper management and control of battery systems, especially for large, high-energy, high-power batteries that comprise many individual cells. To be able to manage a battery pack, we require algorithms or computer methods that continuously monitor the operation of the battery cells and provide information regarding the state and the health of the battery cells to the application that is being powered by the battery pack. And the overarching purpose of the specialization is to learn how to design and to implement these algorithms. This would normally be done using a special purpose computer known as a battery management system, or BMS. A BMS is an embedded system. That is, it is not a general purpose computer, but instead it comprises purpose-built electronics plus custom designed software for the battery management task. The photograph on this slide shows a battery management system that some colleagues at a partner university and we together designed and built for monitoring and controlling a battery system built from commercial plug-in hybrid electric vehicle battery cells. While it's not visible in the photo, the battery cells used by the vehicle are bolted directly onto the circuit boards and are mounted underneath these circuit boards. And the circuit boards that you do see in the photo comprise the electronics of the battery management system. The software or algorithms that we will study in this specialization are implemented on processors located on these electronics circuit boards. In this first course of the specialization, we do not yet look at the algorithms for a battery management system. Instead, we look at the battery management system itself. The primary functions of a battery management system are, first, to protect the human who is operating the battery-powered device, and that is our primary and ultimate concern. Under no circumstances should a human being ever be in danger from the battery pack. The BMS must be able to detect unsafe operating conditions and to respond to them in a way that warns the user and, if possible, eliminates the hazardous condition. A secondary concern for a battery management system is to protect the battery pack itself. We must ensure that the battery is maintained in a healthy operational window under all normal operating conditions. And we must also have fallback safety mechanisms in place in case of abuse of the battery system by the host application or other abnormal operating conditions leading to failure. Our algorithms must continuously monitor the state of health of the battery pack to be able to give guidance to the host application regarding the availability of energy and power such that the battery pack is never overstressed. That is, we desire to extend the life of the battery pack as much as possible, but we also at the same time desire to obtain as high a level of performance as possible from the battery pack. So we do not wish to be overly conservative in our guidance or overly free either. We want to optimize a trade-off between performance and life. Part of this task often requires that we maintain the state of the battery within some prescribed performance window. That is, we may not be permitted to allow the state of charge to ever exceed some level, or on the other hand, we may not be permitted ever to let the state of charge go below some level. So when computing power limits to inform the host application of the availability of power and energy in the battery pack, we must keep this kind of operational window in mind. As already mentioned, an important function of a battery management system is to provide information to the host controller regarding how best to use the battery pack. And this includes providing these energy limits and power limits estimates, but it often can also include telling a host controller what's the best way to charge the battery system right now, and in a vehicle how much range might be available, and many other possible things like that. Very simple battery-powered applications often do not require a sophisticated battery management system. For example, something like a flashlight simply uses its battery until all of the energy is expended, at which time you remove the battery and put in a new battery and throw the old battery into the recycle bin. Or if you were using a rechargeable battery like a nickel-cadmium battery, you would take that out of the flashlight and place it in the charger and charge it and then replace it into the flashlight. There's no need for a complicated battery management system to tell you when to do this. You simply recharge the battery when it's no longer fulfilling its requirement to provide energy to light the bulb in the flashlight. However, all lithium-ion battery packs need at least a minimal battery management system, even in a simple application like a flashlight. And the reason is that lithium-ion battery cells are extremely efficient. While some other battery technologies such as lead acid or nickel metal hydride can withstand some level of overcharging and still remain safe, lithium-ion battery cells cannot be safely overcharged. If a lithium-ion battery cell is overcharged, then at some point it will catch fire and explode. But even for lithium-ion battery systems, we don't necessarily require a complicated battery management system. In some cases, we might be able to get away with a very simple battery management system that merely ensures that the battery cell never has voltage exceeding some maximum level or that's below some minimum level. And this can be done with relatively inexpensive purpose-built electronics that integrated circuit manufacturers have designed for that exact purpose. So we might want to use a very simple battery management system for a low complexity, low cost application. Implementing a sophisticated battery management system requires a significant amount of processing, which means we need a fairly capable microcontroller to implement the algorithms. So there is a cost associated with sophisticated battery management algorithms. At the same time, it's important to understand that simple algorithms and inexpensive solutions will not usually be very good solutions. So there's an important range of applications for which we would like to implement more sophisticated battery management algorithms for better results. And how do we make that choice? And here's a simple rule of thumb or a principle from years of experience that might be helpful to you. I propose that your entire battery system, including the battery management system, is considered cheap enough, inexpensive enough, if when it comes time to replace it, you can no longer remember the last time that you replaced it. The idea is this: I cannot remember the last time I replaced the batteries in my television remote control. So I guess that means that the batteries for my television remote control were inexpensive enough for that application. If the batteries had been very expensive, you know I would have remembered for a very long time exactly when I replaced them most recently. So if you have a large battery, like for a grid storage application or for an electric vehicle, that battery will probably cost thousands of dollars or thousands of euro. And you know that if you had to replace this battery, you would remember for a very, very, very long time when you replaced it, how much you paid for it, and all of the details if you ever had to do so. So if your electric vehicle's battery pack failed, you probably would never buy that same model of vehicle again. So battery packs and battery management systems for electric vehicles should last the entire life of the vehicle. Battery packs and battery management systems for other large-scale applications should last a decade or more without servicing. In order to maximize the life of a large battery pack, it's not possible to use simple algorithms and simple ad hoc methods. We really must use the best methods that we know about, and we must use the best battery cells that we know about, and the entire solution must be as good as we can make it. So large battery packs represent a large investment, and so they motivate the best battery management electronics and the best battery management algorithms that we can afford. So this specialization will focus on teaching algorithms for managing large battery packs. Even so, the methods that you will learn also work for small battery packs. And it's simply a business decision, an economic decision regarding when you use the robust but somewhat more complicated methods instead of using a less expensive but less accurate and simpler method. There are many applications of large lithium-ion battery packs. My research team at the University of Colorado, Colorado Springs has focused for over 15 years primarily on automotive applications. We have looked at some other applications also, but our main focus has been on automotive. So that means that many of the examples that I will share with you in this specialization come from our experience in this automotive domain. If the application that you have in mind is different from this, then you can still gain from this experience, but there will be some distinctions almost certainly in some of the smaller details in how you implement the algorithms. Now, automotive applications for large lithium-ion batteries are a really growing market right now. When I started research in this field in 2001, there were no vehicles having lithium-ion battery packs. And in fact, there were only 2 hybrid vehicles in the United States, and both of these use nickel metal hydride battery systems. Both of those vehicles were hybrid electric vehicles. So they had both a gasoline engine and an electric motor that is powered through the battery pack. The gasoline engine provides the average power demand required by the vehicle, and the electric motor and associated battery system handles the difference between the average and some peak power demand, and also when the vehicle is coasting or braking, it can accept some power from the drivetrain to do some on-demand recharging of the battery as well. The reason that this is helpful is because the gasoline engine operates most efficiently only in a small range of speed and torque. And if we can maintain the engine within that small range of speed and torque, then we can get good fuel economy. The battery and the motor provide the excess power or absorb the excess power so that when the motor and the engine are combined, the power provided is able to meet the load demand required by the driver. The battery and motor operate efficiently over a much wider range of speed and torque than does a gasoline engine. So the overall efficiency of a hybrid electric vehicle can be much higher than an equivalent standard gasoline-powered vehicle. The battery pack for a hybrid electric vehicle can be relatively small. And the reason for this is that the battery pack is not required to provide an enormous amount of energy. It provides very little energy, usually in the hybrid electric vehicle, and the vehicle is not able to drive any distance at all on the battery pack power alone. The battery pack for the hybrid vehicle simply provides the differences between the average and the peak power. So the photograph I show you on the slide is the well-known Toyota Prius hybrid electric vehicle, which started out with nickel metal hydride battery cells, but I believe that in some versions they also are coming with lithium-ion battery cells at this point. Another hybridized vehicle is known as a plug-in hybrid electric vehicle. These vehicles have larger battery packs than a standard hybrid electric vehicle, and consequently they do have some all-electric range. That is, you can turn the gasoline engine off and drive simply with the motor that is powered by the battery system. Plug-in hybrid electric vehicles can get much better fuel economy than hybrid electric vehicles simply because they don't use gasoline as often. And plug-in hybrid electric vehicles usually operate in electric-only mode only at low speeds, and at high speeds we must turn on the gasoline engine in order to meet the demand. The plug-in hybrid electric vehicle on this photo is the Ford C-Max Energy, which has approximately 20 miles range, or about 32 kilometer range, in all electric mode without the gasoline engine running at all. There are a range of sizes for plug-in hybrid electric vehicles. Some have a range of about 10 miles or 16 kilometers. Others have a range of more than 50 miles or 80 kilometers. The larger range versions sometimes operate in electric mode even at high speeds and are sometimes known as extended range electric vehicles. That is, we consider them to be electric vehicles almost all the time because they have full power capability and a fairly decent range capability, but the gasoline engine can turn on in order to extend the range of your electric vehicle just like it does in a hybrid. For most people, an extended range electric vehicle makes a lot of practical sense as their primary vehicle. If your daily commute is less than 50 miles or 80 kilometers, then you can plug your vehicle into the wall outlet at home and never require going to the gasoline station at all. On the rare occasions where you must drive more than 50 miles or 80 kilometers, there's still no problem because there's still the gasoline engine and it will turn on and drive you as far as you want to go. From a battery perspective, extended range electric vehicles are very similar to plug-in hybrid electric vehicles, except they have larger battery packs to be able to store more energy for this longer range, and also to be able to deliver more power so that we can operate in electric-only mode even under full load. And the extended range electric vehicle in the picture to the right is the Chevrolet Volt, which has an all-electric range of about 53 miles, or a little over 80 kilometers. So you can see that we're progressing from hybrid electric vehicle to plug-in hybrid electric vehicle to extended range electric vehicle, and in every step of the progression the gasoline engine is used less and the electric power from the battery is used more. So the ultimate conclusion is a pure battery electric vehicle where we remove the gasoline engine entirely and leave a vehicle that's powered only by its battery and electric motor. And so people call this an electric vehicle or sometimes a battery electric vehicle. These vehicles have the largest battery packs because they must rely exclusively on the battery energy for range and for power. The electric vehicle in the picture on the right is the Tesla Model S, which in many of its configurations has over a 300-mile range. And remember I said in 2001 there were only 2 hybrid electric vehicle models in the United States, and neither were lithium-ion? Well, the founder of Bloomberg New Energy Finance, Michael Liebreich, has said by 2020 there will be over 120 different models of electric vehicle across the spectrum. This isn't just hybrid electric vehicles or plug-ins. This is pure electric vehicles. These are vehicles that have already been announced by the manufacturers. He continues by saying these are great cars. They will make internal combustion look old-fashioned. So this market is seeing incredible growth, and there's a demand for engineers who can build battery management systems and who can write battery management system algorithms. All of these vehicle applications we've looked at use battery packs that are large in some sense. Clearly they are larger than the battery in your mobile phone. These applications also use batteries that are high voltage. For example, a laptop battery might be on the order of 15 volts. A cell phone battery might be on the order of 4 volts, but a vehicle battery is usually between 250 volts and maybe even 600 volts or higher. Vehicle applications also require high electrical current, often over 1,000 amperes under peak load. And this is very different from a portable electronics application where much less current is required. So even though there are some distinctions in design between the battery systems required for a hybrid electric vehicle versus a battery electric vehicle, the commonalities are more significant than the differences. So we're going to look at the distinctions in design only when we need to do so. But more often we will look at fairly generic battery pack design with fairly generic algorithm requirements that it can apply to any type of battery application. And so when I talk about a vehicle application where we don't really need to make distinctions between what kind of battery-enabled vehicle we're talking about, I will simply refer to the whole class of electrified vehicles as XEV, where X could be H for hybrid or PH for plug-in hybrid or ER for extended range and so forth. Of course, there are other large-scale applications. For example, there are emerging applications where the utility grid uses large batteries for different purposes. One is for storage. We can store excess generating capacity in a battery system for later use when the grid load exceeds generating capacity. Now, batteries may not really be the best choice for grid-scale energy storage. Something like pumped hydro might be a better large-scale solution. But there are still cases where grid storage does make sense, such as for remote locations where microgeneration is done. Another example large-scale utility application is for grid backup. Suppose some maintenance must be done on a local power distribution station. Normally, your entire neighborhood would be without power while the maintenance is being performed. But if a large mobile battery pack, perhaps on the trailer of a semi-truck, were to be connected to your neighborhood while the neighborhood is disconnected from the power station, then your neighborhood could receive power while the maintenance is being done, and you would never even know that there was a power outage at all. Another grid application is known as frequency regulation, which deals with relatively small amounts of excess generation capacity or excess load and buffers the grid against large power swings over a relatively short time scale of the order of minutes rather than of hours or days, as the grid is often scheduled. So all of these grid-type applications are being investigated by utility companies, even though not very many have been implemented at full scale at this point. But it appears to be quite clear that there will be some future application of lithium-ion battery systems on the utility grid.